This is Barry from Imagination to Reality CNC, and in this video we're going to go through CNC tooling and the collet system and how to do it correctly. So the i2R CNC machines are CNC routers, which are primarily used for machining non-ferrous materials such as wood, plastics and light metals like aluminium, copper or brass. And to do this effectively, we need to ensure that we're using the right tooling. And that's where things get a little bit difficult because there is such a vast array of tooling available, and how do you know the right ones to choose? In general, any solid carbide CNC end mill will cut all of those materials. But the differences between one tool and the next is how the edge geometry has been optimized to effectively remove that material, be it timber, plastic, or soft metals. As a general rule of thumb, if working with plastics or soft metals, we look for a single flute solid carbide router bit. If I was to show an example of one of these, you can see there is only one cutting edge or a single flute going through the diameter of the tool. This cutting tool is optimized for working with plastics or softer metals. When working with timbers, it can be generally said that we're using a 2-flute solid carbide end mill. And as the machines get bigger and more powerful, you may see 3-flute and 4-flute end mills. If we were to dive a little bit deeper into the tooling available, I have an example here of 2 6mm end mills. Both have 2-flute cutting edges. But in particular, there is another term that I'd like to introduce to you called an upcut or a downcut. Looking at the 2-flute upcut router bit first, if I was to hold it in the same orientation that it would sit in the spindle, as it's rotating clockwise, as does the CNC spindle rotates, you can see that the flutes are spiraling up towards the ceiling. That's known as an upcut router bit or a spiral up router bit. The advantage of a spiral up router bit when used in timbers is that you can machine a very deep slot and it will effectively remove all the chips up towards the surface of the material. The downside of using an upcut router bit is that with that upward spiral and all the material shooting up through the slot, it is prone to giving a damaged upper edge or chipping the upper edge of your cut. That's where the opposite geometry, a 2-flute downcut router bit comes into play. You can now see that the spiral on these cutting tools is spiraling down towards the table. The advantage of the downward spiral is it reduces that tear out on the surface of the material. But the trade-off is that if you were to do an aggressive cut or a deep slot, it's also forcing all that swarf down into the material, which does not allow for effective chip removal, which eventually may overheat the bit and potentially break it. So if using a downwards or a downcut spiral cutting tool, you have to reduce your pass depth to be something reasonable in comparison to the upcut spiral bit of which you can do an aggressive cut. The next cutter we're going to look at is one of my favorite, and this is called a compression router bit. So looking at this cutting tool rotating clockwise in the spindle, we can see that there's a portion towards the tip of the cutting tool spiraling up, and then it changes to the rest of the cutting tool spiraling down. It's important to understand this process because when using the cutting tool, if your depth of cut is not great enough, you are not getting to utilize both the upwards and downward portion of this cutting tool. In the sample we cut here, we have set the depth of cut to only engage with the upwards portion of the cutting tool, and you can see a result of the finish when the depth of cut is not great enough is tear out on the surface of the material. As we increase the depth of cut such that we're using the downwards portion of the cutting tool as well, you can see that there is less tear out on the surface of the material, and this is the intended purposes of a compression router bit. Normally the change in geometry between the upwards and downwards portion of the cutting tool happens at the diameter of the tool. So for a 6mm compression cutter, we need to cut our first pass depth or our depth of cut greater than 6mm deep. So anything like 6.5, 7, 8 or 9mm would be a suitable first pass depth of cut for a 6mm compression router bit. Another geometry after we've gone through our single flute for aluminium or plastics. We've got our 2 flute up and down for timber. Another bit you may look to use as well is called a ball nose router bit. This ball nose has 2 flutes, again, which is suitable for timber. But the tip geometry of this cutting tool, it has a radius to it of which is the same radius associated with the width of the cutting tool. A ball nose routing bit is primarily used for 3D profiling your material, and in the case of this cutting tool, it's 3D profiling timber. Another bit we commonly recommend you get with your CNC router is a V-bit. Looking a bit closer at this V-bit, you can see that the angle of the V-bit, and when spinning at a high speed, the shape it's going to leave in the material will be a V shape. This tool is very useful for putting simple chamfers or bevels on your material after cutting, but also for doing an operation which we'll touch on later in a different video, V-carve engraving of signage. One last cutting tool that you shouldn't leave out of your inventory is a large surfacing bit. You can see with this cutting tool, again it has 2 wings, but it's a very large diameter, and this is used for surfacing any material and or your spoil board. Another offering from i2R CNC also is something known as their 8-bit router set. This is a good entry-level set for a user to buy if they're not really sure which bit to start off with, because it contains all those geometries we've just discussed. Primarily these cutting tools are for working with timber only, and if you were looking to work with aluminium or plastics, you should consider buying additional bits such as the ones we've discussed earlier. Please note if you do buy the 8-bit set, that some of the larger insert bits do have a wax coating on them, and you should peel that wax coating off with your nail. Moving on in this video, now that we've discussed the major geometry of the cutting tools available, we need to understand the mounting system in the spindle for holding those tools. The i2R A-series CNC router comes with a 2.2 kilowatt water-cooled spindle and specifically an ER20 tapered collet. The ER20 is the external shape or taper of this collet that fits into the spindle. Other options available, such as for the i2R B-series, is an ER16 collet. It has a similar angled taper, but the entire body of the collet is smaller. And these are not interchangeable. You must use an ER16 collet with your ER16 spindle, or you must use the ER20 collet with the ER20 spindle. Outside of that, these collet systems, the ER20 collet system, does come with a range of diameters on the inside, of which can fit smaller or larger shanked tools. In summary, it is critical that if the shank of your cutting tool is a 6mm shank, you must use an ER20 6mm collet for it to be fitted in. You should never mix up your metric collets with your imperial collets, despite how close a match you believe they are. A 1/4 inch imperial collet is 6.35 of a millimeter, and this 6.35 millimeter collet should not be used for a 6mm shank tool. You should look to get a 6mm collet for a 6mm shanked tool. Moving on from that is understanding how the collet system works with your spindle. And here, by hand, I'm just using my hand. I don't need any spanners to undo the collet nut assembly. And you will find, as you've just purchased your CNC machine, that there's already a collet in there. So the i2R A-series comes with a 1/4 inch collet and 1/2 inch collet as standard. The 1/4 inch collet and the 1/2 inch collet matches perfectly with your 8-bit set. But if you did buy some additional tooling, you would look to buy the collets that suit the shank size of the tool. The first step you're going to present yourself with is the collet nut and the collet are already assembled together. Now you need to remove the collet nut out and make sure the assembly has been done correctly. To do this, I like to place my thumb on the collet inside the nut, and on the other end I put some pressure to one side or the other, of which then I can see that the collet pops out. You always want to check inside your collet nut that it is free from dust or debris. And what I like to use to do this is an old toothbrush, or if you do have compressed air in your workshop, you can blow it out with compressed air. But it is imperative that the inside face of your collet nut is clear of all debris. The same can go for your actual collets. The ER20 collet system has a series of open slits in it, And this allows for the clamping mechanism to hold on to the shank of your cutting tool. If these open slits are full of dust or debris, the collet system will not work effectively and you won't effectively clamp your tool. So it is also important to either use that toothbrush or the compressed air in your workshop to blow out any dust or debris that is inside the openings of the collet. The next step, when you've ensured you've selected the correct collet and you've made sure that the collet nut is clear of dust or debris, you can proceed to place the collet in the nut. As you can see right now, it is free to sit wherever it wants, and this is not correctly seated. To correctly seat the collet in the nut, you can push with some pressure the end of the collet towards the front of the nut, and you know it now has seated correctly because you can hear a click. Another method I like to use to double check is when I turn it upside down, the collet does not fall out of the nut. This verifies to me that the collet and nut assembly is correct. Now you can proceed to place your cutting tool in the collet. Do note with your cutting tool that there is a shank area that's clear of the flutes. And you should not over collet your cutting tool such that any of the collet is covering up the flutes of the cutting tool. On the contrary to that, you do not want to over collet where you do not grip enough of the shank. So if I was to give a rule of thumb, you should have at least as much of the shank up that covers half of the actual collet itself. So I'm going to proceed to place the shank of the tool in until I can look from the other end and I've at least gone halfway through the collet. When we get to that step, we can now place the collet, nut and cutting tool assembly towards the spindle. At this stage, I prefer to hand tighten the collet and spindle together until I start to feel some resistance. I do not use the spanners at this stage because if you do and the threads are not correctly seated, you may cross thread the threads on your nut or your spindle. Once you have hand tightened the collet nut all the way up and you start to feel some resistance, we know the assembly is correct and we're ready to move on to our spanners. Note that both spanners are absolutely identical, but at one end there's a small end and at the other end there's a large end. The small end of the collet spanner is used for holding the shaft of the spindle, and the large end of the spanner is used for holding the collet nut. When you've got both of them seated on correctly, you can proceed to tighten the collet nut. You can see that it took very little turn before the collet nut got tight. And I only use the strength in my wrist for that tightening action and try and refrain from using my upper arm or my shoulders. A tight nip of the collet nut assembly is enough to securely hold the tool in place, and that really does assume that you have followed that process correctly and that the collet nut is seated correctly. If we were to reverse this entire process when we get to a stage that we want to remove the tool, again, we can use our spanners, the small end to hold the shaft of the spindle and the large end to hold the collet nut. As we only use the strength in our wrist to tighten up this assembly, it should be relatively easy to break that seal. I want to show you now that if I continue to loosen the nut by hand, I've managed to get 2 turns before the nut has got tight again. The reason for this is there's a double locking thread on the collet nut. A double locking thread ensures that if you were to forget to tighten the nut up and start the spindle, the nut would not fly off. To get past that second locking nut, you will require the spanners again just to break that little seal. And you can continue to proceed to do that the rest of the way by hand. And reversing the process completely, I place my thumb on the face of the collet and I push the other end of the collet to one side in the nut assembly and it pops out. And that is how you correctly seat and unseat and load a tool into your CNC router. One thing I'd also like to touch on just to show you ways not to collet and things not to do. Your collet system will not work correctly if you put the collet in the spindle first and then proceed to tighten the nut up. The real goal with an ER20 collet system is that the collet must be seated in the nut first and pressed into place until there's a click. Another common mistake made by users is that they may place the cutting tool inside the collet first and then proceed to put the nut in place. With the cutting tool inside the collet cannot compress enough such that it seats correctly into the collet nut. So this is a big no-no. The last topic we'd like to discuss in regards to CNC tooling and collets is maintenance and the fact that they are consumables and they do need to be replaced. With your CNC tooling, as the blades of your CNC tools dull, you will start to notice degraded cutting on all your material, and that's a sure sign that you need to replace your tooling. The collets themselves are consumables also and do need to be replaced after 300, 400, 500 hours of machining. And it really depends as well on how often you change that tool. Every time you tighten and loosen the collet nut up, you are fatiguing the actual collets themselves. There is a bit of a spring mechanism in them, and the more you tighten and loosen up that spring, the more it tends to fatigue. It will get to a point with your collets that if you don't replace them on a routine basis, it will affect the concentricity of the assembly of the collet, the nut, and the cutting tool. With a poor collet concentricity, you will find things that you're breaking cutting tools a lot sooner, but also probably not as obvious because it takes time, is that the cutting tools are wearing out. So like I said, your cutting tools are consumables, your collets are consumables, and they should be replaced at routine intervals. The last thing noting from a maintenance point of view is the collets are made of a high-speed steel. There's absolutely no form of rust prevention on the collets, and it's not a bad idea on routine intervals as well to put a light machine oil on top of the collet to stop any rust or pitting forming on the surface. The same thing goes for your spindle. The spindle shaft itself is a high-speed steel that is not protected from rust, and there's no harm ever in rubbing a light machine oil inside the spindle as well to prevent any rusting from forming between the collet and the spindle itself. So that concludes the video on CNC cutting tools and how to use the collet system correctly on your i2R CNC router. Please check out our other videos which will explore other aspects of this machine and how to use it correctly.